가보셨나요?
아니요, 지금 처음 봤습니다.
라이브네요. 라이브니까 지금.
예. Do we have a first speaker? Dr. Itamar Alali?
Yep. Hi.
Hello. I think you can share your slide so that we can start on time.
Is that okay? Can you see it?
I can see it very well. Yeah.
Great, thanks.
Just to make sure to the speakers, you'll be given 15 minutes time for presentation and then 3 minutes of question and answer. And then we'll have 2 minutes for transitions. So I'll give a reminder to the speakers, something like 2 or 3 minutes before your 15 minutes end. Okay. And I was informed by the organizers that all the questions from the audiences should be through the text. This chatting, you text your questions through chatting window. If the speaker sees it, one can just answer. If the speaker doesn't notice the question, I'll give a notice about the question. Okay. Good. So we'll start after 25 seconds or so.
Okay.
Okay, welcome everybody to the Strings and Fields parallel session. The first speaker will be Dr. Itamar Alali, and I think he will be talking about gravitational decoherence and dark matter. Please.
Yep, that's right. Thank you so much, and thank you to the organizers as well for putting together this great conference. It's the first day, and I'm looking forward to seeing what we have for the next few days. So yeah, my name is Itamar. I'll be talking about gravitational decoherence, as you said, with some applications to dark matter. And this is going to be based on these papers here, which I wrote with my advisor, Professor Mark Hertzberg at Tufts. So let me get started. So I'll just be talking a little bit in the beginning about the motivation for this work and why we set out to answer this question. And then in order to discuss decoherence, it's going to be important to characterize the way that the dark matter will interact with its environment. So that'll be the next bit. And then finally, I'll discuss some of the results and the implications of this work. So first of all, why is this an interesting question? What is the question I'm trying to answer, and why is it interesting? Well, we know from quantum mechanics that matter can exist in superpositions, and specifically in sort of macroscopically observable superpositions. Sometimes people refer to these as Schrodinger cat states. Now, of course, we don't see these in everyday life. And one of the main reasons for that is because of decoherence. In fact, most matter interacts very frequently with its environment. And so decoherence happens very rapidly, and you don't see cats that are both dead and alive in real life. Now, what's interesting about gravity is that because gravity is such a weak force, it is possible that matter that interacts only gravitationally would have long-lived quantum coherence because the interactions are just not enough to lead to rapid decoherence. And so this is sort of the genesis of this idea that since, at least for now, we know that dark matter at least primarily interacts through gravity, it's possible that a Schrodinger cat state, like the one represented here pictorially by this red and this blue distribution, some kind of macroscopically differentiable state, superposition state, could have long-lived quantum coherence. Specifically, when we're thinking about this, in a few moments, I'll be applying it to the case of axion dark matter. And for the purposes of this work, axions are just a scalar particle, which is treated classically or semi-classically as a scalar field. And so then the question will be, what is the rate of decoherence for an object of this type? So in order to answer that question, we need to discuss the way it interacts with its environment. So what I'm imagining is this Schrodinger cat state of dark matter made up of some state 1 and state 2, which is existing somewhere out in the galaxy. And then some particle in its environment will simply pass it by and scatter off of it. And so because the probe particle, which is here represented by psi, is scattering off of this superposition, psi will itself evolve into a superposition. And so it becomes inevitably entangled with the dark matter. And so the full state of the system will look something like this, where there's an entangled state between the dark matter and the particle. And then in general, I can represent this state by its density matrix, but an observer which is observing this dark matter from outside of the system would see these probe particles come in and out all the time, and there would be so many degrees of freedom to the environmental particles that they would simply ignore them and only pay attention to the dark matter. And so this amounts to performing a trace over the state of the particle, which then leads me to this reduced density matrix, where I have the two diagonal elements of the matrix, which represent sort of classical probability distributions, and then the off-diagonal elements, which encode the quantum behavior. So in this case, if you think of sort of a simple superposition, which has some kind of interference phenomenon, that would be encoded in the off-diagonal elements of the density matrix. And the existence of these elements is controlled by this inner product right here, which is the inner product between the state of the particle, which scatters off of one of these dark matter states, and the state of the particle, which scatters off of the other dark matter state. And so then the measure of decoherence is how quickly these off-diagonal elements will disappear. So to describe this, we can just think of this particle scattering and treat this in perturbation theory. And so the state of the particle after the interaction is some unscattered wave function and then some scattered wave function. And so then it turns out that the most important part of this inner product is just going to be from the scattered wave functions. And so the decoherence rate will be proportional to this, where there's some overlap between state 1 and state 1, state 2 and state 2, and then a cross term between states 1 and states 2. And so the full decoherence rate, when computed rigorously, is proportional to the number density of the probe particles, the speeds of the probe particles, the typical speeds of the probe particles. And then these sigmas are, I'll introduce them in a moment, but these are essentially scattering cross sections. They're generalized because there's this cross term, which is not quite a cross section, but it's something like a product between two different scattering amplitudes. But so this should sort of look familiar, and V sigma is a typical process rate that you would see in the literature, specifically in the context of decoherence. But so in order to fully describe the evolution of the probe particle state, we need a Schrodinger equation for this. And the difficulty here is that you need a Hamiltonian, which can encode the general relativistic gravitational interactions that the probe particle undergoes with the dark matter. So ignoring spin for simplicity, I can treat a scalar field for the probe particle, although the typical probes I'd be considering should be something like baryons or photons in the galaxy. The first approximation, a scalar field will do it. And so this is the action for a scalar field minimally coupled to gravity. And what's important to note at this point is that at the level that we're doing this calculation, this is all being treated very rigorously in effective field theory. So it's sort of a truly quantum gravity calculation, which is sort of rare to find calculations you can do where quantum gravity doesn't have any trouble, but can be done in a rigorous way. And so taking just the simplest metric you can think of, which is just a diagonal metric with these phi's and psi's, which are generalized Newtonian gravitational potentials, we find this Hamiltonian, which has a relativistic kinetic term plus these, which we'll refer to as potential energy terms. And so the sort of important part of all of this is what are the results? How do we begin to characterize the decoherence of these funny dark matter states in our galaxy? So it's important to, first of all, decide on what kind of state you want to study. So for example, if I have a static configuration of the dark matter, so similar to the image I showed of the red and the blue mass distributions, then the problem is very simple. It's just a simple scattering calculation like you would see in a quantum mechanics textbook. So this would be the response, the scattering response of the Q, the mode of wave Q of some wave packet. And it's just the usual thing, a spherical wave, a scattering amplitude, and then the Schrodinger time evolution. And the only difference is that the scattering amplitude is defined in this sort of slightly generalized relativistic way. So you can see how in the limit, the non-relativistic limit, you would just pick up a Newtonian potential and a mass, and it would look just like the usual Lippmann-Schwinger equation. And so here's that generalized cross-section from before. So you can see it's really just a regular scattering cross-section, with the exception that I can have the 1-2 term, which is this funny cross term. And so I come up with this decoherence rate as before. So to look at an example, you can imagine that maybe this Schrodinger cat state is made of just a random fluctuation of the dark matter density in the background of our galaxy. And let's say this random fluctuation is approximately a Gaussian, and it evolves itself into some kind of superposition, then the scattering amplitude would also be a Gaussian, and the decoherence rate would scale in the following way, or at least the leading order term would. So as you may expect, it scales with the densities of both the dark matter and the probe particle. This makes sense. The more dense the region is, the more frequent the interactions are, the quicker the decoherence. But what's interesting is that it has this very dramatic inverse scaling with the mass of the dark matter particle. So depending on what kind of dark matter you're thinking of, the results can be very different. So taking a look at this briefly, what I have here is the inverse decoherence rate. So really you can think of this as the time it takes for decoherence to occur. Strictly speaking, that time should be, you should integrate over the process, but just the inverse of the rate gives us a good guess. And so in the galactic halo, in the sort of a typical spot of the galactic halo, we can see that for masses which are relevant, for example, for the QCD axion, the typical decoherence rate is right around the age of the universe, maybe a little bit longer, or so, sorry, the decoherence time is a little bit longer than the age of the universe. And so you wouldn't expect decoherence, but for most masses, as you go to lighter and lighter axion masses, if axion dark matter is what you're considering, you would expect decoherence to occur. And then this green curve similarly is, if you look at instead in Earth's atmosphere, maybe this would be relevant for ground-based detection experiments. And so you can see that the decoherence is much more rapid in the Earth's atmosphere. Another example, instead of considering a static source, a slightly more interesting example maybe is that of an oscillating scalar field. So when you think of typical light axion dark matter, usually you're expecting a coherently oscillating scalar field. And so if we think of this thing in that way with some spatial profile and then some simple oscillatory behavior, the scattered wave function becomes a little more complicated. It has three pieces. This alpha equals 0 piece is more or less the same as in the static case. It's just a spherical wave, the scattering amplitude, and the Schrodinger time evolution. But then these -1 and +1 are additional contributions to the scattering, which come from essentially this oscillation giving the particle a kick forward or backward in momentum. And so you have additional support in the probability distributions for slightly higher or lower momentum, so that the collision becomes slightly inelastic. And so what you can have in mind then is something that looks like this. If it'll go, let's try that again. Well, I guess it's not cooperating. Okay, so what I have in mind, oh, there we go. We got something to go, is a similar mass distribution as we were thinking of before, but where the superposition is now in the phase of the axion's field. So it's not, it doesn't have any difference in the superposition states with the distribution of mass, but rather the phase of oscillation is slightly out of phase. And so this might be slightly more of a nuanced superposition, which may last longer. And so considering that superposition, there's all these details in terms of the dependence on the actual phase of the field. But the most interesting part is to look at these generalized cross sections here, which the only contributions that remain in this decoherence rate are these +1, +1, -1, -1, -1, +1. So if you recall, those corresponding to the alpha equals -1 and +1 in these scattering amplitudes, these are the pieces of the solution which either received a forward or backward kick in momentum. And so none of the contributions to the decoherence rate are related to the just typical usual scattering off of this mass distribution, but rather the particles that receive this kick. And so if we look again at the Gaussian example, you have that these scattering cross sections are still proportional to Gaussians. And importantly, the argument of the Gaussian is a transfer momentum. And so if the only contributions to this decoherence rate come from momenta that get a kick, then this transfer momentum will never vanish. And so in fact, this decoherence rate could become exponentially suppressed if this factor is big enough. And so if we just look at typical slowly moving dark matter, taking the non-relativistic limit of this, it's just the inverse square of these, the speed of the axion particles and the speed of the probe particles. And so indeed, this is a very big number. And so the decoherence rate becomes exponentially suppressed. So what this means is that if we have dark matter in the galaxy, which is in a superposition of just the phase of the axion field, we don't expect it to decohere. It would just sort of stay in that superposition for a very, very long time. Now, on the other hand, if we can come up with a truly relativistic configuration, which involves fast moving particles, we may achieve rapid decoherence of that object. So very briefly, let me just mention examples of where that could be. So in very dense boson stars, the axions that would make up these boson stars would be ultra-relativistic. And so for this mass and radius of the boson stars, for the dense boson stars, they scale inversely with the mass in this way. We would find a decoherence rate that looks something like this. So it's pretty quick. And then, of course, as you make the axion mass even lighter than 1 electron volt, this just gets faster and faster. And so we would expect appreciable decoherence. And lastly, near a black hole horizon, there's just generically going to be very high speed particles and high density. And so decoherence will happen very quickly. What's interesting about that is that if there's rapid decoherence near the black hole horizon, that means that any sort of Schrodinger cat state, which is very quantum living out in the galaxy, once it gets eaten by a black hole, as it approaches the horizon, it experiences decoherence. And then the state that crosses the horizon is going to be the most classical state. So this might have some implications for black hole information paradox, just thinking about what kinds of states cross the black hole horizon. Okay, so just to conclude, I hope I convinced you that looking at gravitational decoherence is sort of a non-trivial thing to do, and that dark matter is special because it doesn't necessarily decohere as quickly as ordinary matter, and specifically that superpositions of the phase of scalar bosonic dark matter, light bosonic dark matter like the axion, may live for a long time. And then one just quick extra note is that this might also have implications for direct detection experiments. So for example, the resonant cavity haloscope experiments like ADMX, they have a resonant cavity which, when interacting with the axion, produces a resonant signal in the cavity, and it should be sensitive to the axion's phase. So if indeed a superposition state were to interact with this detector, maybe they should be considering something like a superposition of axion waves to try to look for an appropriate signal. So thank you for your attention. Thanks for the time, and I'll take any questions if you have any.
Yeah, thank you very much. Any questions? I don't see any question in the text yet. So I guess your approach is applicable to dark matters which only has gravitational interaction within the dark sector.
Yeah, or at least is
not all dark matter
primarily.
models.
Yeah. Yeah, we did consider, self interactions in the dark matter for sure. And for example, an axion should have some self interactions. But to first approximation, the sort of the first line of defense will be the gravitational interactions. And so for most of these cases, appreciable decoherence is seen, gravity is enough. In the case of the phase superposition, sort of the next step would be to look at whether self-interactions will do this or not. Yeah.
Okay, there's one more question. Can you read this?
Yes, the self-interactions for axion dark matter with a different phase superposition is very interesting. What is the realistic initial state for these ultralight dark matter models? What can make its quantum superposition? That's a good question. So one thing to think about. So first of all, the sort of premise of the work is we sort of just assume that such a state can exist and to see if it would live long. Once you can see that some of these states live long, it becomes more interesting to consider how they come about. And so, for example, there's some work in the literature that's shown that systems that exhibit any form of chaos, so for example, just billiard balls scattering on a billiard table, if you just let billiard balls go through many collisions and you turn off decoherence, the wave function of a billiard ball would spread enormously, and they would become in these sort of fuzzy superpositions. So you can imagine that if decoherence isn't rapid, just infrequent interactions, but nonetheless collisions of dark matter particles somewhere out there exhibit some form of chaos, and so then their wave functions sort of spread, and eventually they become these fuzzy states. Since they're not engaging in very frequent interactions, they don't experience decoherence frequently. So that's all sort of part of the assumptions of the system. So it becomes now more interesting to see, is that a sort of robust setup? Can you really see that happening? Yeah, it's a very good question. Thank you.
Okay, so thank you very much, Tamar, for the nice talk. And thank you very much. Do you have a next speaker, Jacob? Yes.
Yes. Hello. Can you hear me all right?
Yes. Yes. Can you share your screen, please?
Yes.
Okay. So let's just start. The next speaker is Jacob Litterer. He'll be talking about Lorentz invariance from locality of massless spin 2. Please go ahead.
Hi. Thank you, and thanks to everyone for being here at various times. Yeah, today is still June 13th for me. Might be June 14th for other people. So that's right. I'll be talking about a way in which you can derive the Lorentz invariance in theories involving massless spin 2, just from the basic notion of locality. So before we get into that, oh, I don't see, okay. Locality is sort of and Lorentz invariance are very fundamental seeming principles. So we should review what are maybe some principles that are considered fundamental. Certainly some symmetries, rotations, and translations. Some notion of locality we would like to say is fundamental. And in quantum theories, unitarity. But we also have an other symmetry under Lorentz boost invariance. And if you include that, then this idea of locality is sort of has a one-to-one correspondence with causality. And so I would like to wonder, can we possibly relax the assumption of Lorentz invariance in fundamental theories? Can we write down a theory that satisfies these other principles, doesn't have any pathologies, but doesn't have Lorentz invariance? Or can we derive Lorentz invariance from some other principles? And I'll eventually talk about spin 2, but maybe to explain the idea here and kind of motivate this, I'll first talk about spin 1. So there's been a significant amount of work on this already. So in particular, Kostelecki and collaborators have developed this idea that Lorentz invariance is actually not required in the standard model, and you can relax that symmetry without breaking any other nice features of the standard model. So in particular, one way to think about that is that the speed of light could be some different number in each for each particle in the model. So the photon could have some speed c, the electron could have some speed c, etc. And these don't all have to be the same. So in that sense, you could sort of say each sector is Lorentz invariant, but of course the whole theory is not Lorentz invariant. And the amazing thing is that you can do that without causing any other problems. All right. And so the way that I'm going to be talking about locality, so in the context of spin 1, if we look at the locality of the theory without assuming Lorentz invariance, so if I just write down a theory of a single spin 1 particle, so like electromagnetism, without assuming Lorentz invariance, and write down every unique operator at leading order, and then just look at a leading order process, like some 2-to-2 scattering process that exchanges one photon. And I just ask that that process satisfy a basic notion of locality. Then it turns out that the photon sector has to organize to be completely standard, just f squared. So that part of the theory, you could say, is Lorentz invariant. But in the matter sector, it does not need to be Lorentz invariant. You just need a conserved charge. So apparently you need some U1 symmetry of the theory. So the usual U1 of electromagnetism, but the theory doesn't have to be Lorentz invariant to be local in this basic sense. And so that's kind of the approach we want to take for theories involving spin 2 as well. And say, will this be more interesting? And yeah, it turns out we can dramatically improve on these results if we consider spin 2. So let's get into that. And to begin, we can just quickly review the usual Lorentz invariant theory. So here I've just taken the Einstein-Hilbert action and expanded around a flat background to quadratic order. And here the graviton field, h mu, is coupled to the energy momentum tensor of the matter sector. And now one way to see that this theory is local is by looking at this kind of process. So 2-to-2 exchange of some matter particle that exchanges one graviton. And here I've written out the exchange action for this process, which is essentially just taking this interaction term and replacing the h mu using the classical equation of motion. And on the second line, I've just broken up the energy and momentum tensor into its spatially covariant pieces in anticipation of the next few slides. But either way, you can see that this is local just because the only operators here are these inverse box operators. And so this tells you the graviton just propagates at a finite speed, which is the speed inside this box operator. And so the theory looks very nice. And by the way, this is also a gauge invariant way to see that the theory is local. So this is the approach that we'll take when we relax the assumption of Lorentz invariance in this kind of theory. So, all right, how do we do that? So I'd like to construct a theory for spin 2 with 2 degrees of freedom that does not assume Lorentz invariance. So I should be clear about what things I am assuming. Well, we want to talk about spin 2. So we need to keep rotation invariance. And I'll also assume the usual form of the coupling like I had on the previous slide, except this T mu nu that I'm coupling to is not the energy and momentum tensor. So in particular, it does not have to be a conserved object. It's just some rank 2 source. And then if I write down all of the leading 4-dimension operators, then I get something like this, which is basically just what I had on the previous slide, broken up into spatially covariant pieces And I inserted some coefficient in front of every term. And you can also include up to 5 unique mass terms, which I'm just not writing here for brevity, but we also considered those. And right now, if you do this kind of, if you break Lorentz invariance in this way, if you deform the structure of the theory in this way, then you also give up the usual gauge redundancy in GR. So we now have more than 2 degrees of freedom, but we're choosing just to study 2 degrees of freedom. So we have to impose some condition on this theory that cuts down to the number of degrees of freedom that we want. And of course, there's not a unique way to do that, but it turns out in every possible choice of conditions to do that, you'll end up with the same results. So in the next couple of slides, I'll just use the simplest condition, but that's something to keep in mind. So, right, the convention here I'll also mention is that when all of these coefficients are equal to 1, then this just collapses to the structure that I showed on the previous slide, just GR. But if we just assume that there are some real coefficients, then this theory does not satisfy Lorentz invariance. So that's our starting point. And now, so I'll again consider this kind of process where 2 matter particles just exchange a graviton in this theory. And we can write down the exchange action, so from the equations of motion. And now we can see that there are several non-local terms here. So we have all of the terms that I showed from GR, all of these local terms, for example. And now we have some terms that have inverse Laplacians. So these are instantaneous, which make the theory non-local. So if we want to require that this theory be local, you can see that this will give us some conditions on these coefficients. So these A1, 2, 3, etc. are just some combination of the coefficients from the action, and some are more complicated than others. So requiring that the coefficient of the non-local terms vanish gives us some conditions on the coefficients of the action. And like I said, this was the simplest way to cut down to 2 degrees of freedom as an example. And it turns out in every way that you can of cutting down to 2 degrees of freedom, you'll end up with the same conditions on the coefficients of the action. So you'll get the same results. So let me summarize what those are. So just requiring this basic notion of locality, there's no instantaneous terms in the exchange action. We find, well, first of all, let me come back to those mass terms that I mentioned. If you include all the 5 possible mass terms, then for 2 degrees of freedom and locality, all of those mass terms have to vanish. So let me be clear that, of course, in Lorentz invariant spin 2, just requiring 2 degrees of freedom requires the mass to vanish. If you don't assume Lorentz invariance, then you can actually have 2 degrees of freedom consistently, but still have mass terms in the Lagrangian. So it's actually locality that requires those masses to vanish. And then also requiring that the exchange action is local. All the coefficients in the Lagrangian have to organize such that the graviton sector is fully Lorentz invariant, so it collapses back into the GR form. But then additionally, so further than with spin 1, the matter sector also has to be Lorentz invariant. So we can identify this source T mu as being the energy momentum tensor of the matter sector. And yeah, we can show that this explicitly must be conserved. So the only conserved rank 2 tensor in the game is the energy momentum tensor. So just to summarize this result, this kind of amazing in some sense that with spin 1, so you're just talking about a single spin 1, so like a single photon. This basic notion of locality only requires that we have this global U1 symmetry. So just the usual U1 of electromagnetism. So they conserve charge, but the theory does not have to have Lorentz invariance. But if we include spin 2, then not only does the graviton sector have to be Lorentz invariant, but whatever matter sector that it's coupled to also has to be Lorentz invariant subconsistently. So this gives us a new picture of kind of the reason nature is Lorentz invariant, which is that everything is coupled to gravity. And to do that, it has to be Lorentz invariant, assuming locality as a fundamental principle. And so it's sort of emboldened by the strength of this approach, we can try to relax some other symmetry. So if we go back to that fully general theory that doesn't assume Lorentz invariance, if we also relax the assumption of time translation invariance by making all of these coefficients arbitrary functions of time, and we can try to play the same game in that theory, and it will go sort of the same way where you have to cut down to 2 degrees of freedom, and there are multiple ways to do that. But if you just take the simplest approach, so starting from a flat background and doing the same thing, you again find that these coefficient functions have to organize so that the theory is Lorentz boost invariant. However, there's some residual breaking of the time translation symmetry. So after requiring locality, you get back GR plus some other terms with a coefficient that is explicitly a function of time. And this alpha here is just some real coefficient. And it turns out that working to the same order that we've been working to, just a leading order, these extra terms are simply the Gauss-Bonnet terms. So this is how you would usually write it. So these curvature squared terms. And without a function of time here, this is just a surface term in 4 dimensions. So we usually don't include it when talking about GR, although it satisfies all the same symmetries as the Einstein-Hilbert action. With a function of time here, this is not a surface term, and we can include it. And then working to leading order, we can identify these extra terms we're left with as identical to the Gauss-Bonnet terms, where this alpha t is related to this function of time by this relation. And we're not totally sure what to make of that. Why locality would prefer to have the Gauss-Bonnet terms as well instead of only the Einstein-Hilbert terms. But yeah, so that's what we end up with. And as I said, we restricted to a flat background here, but it's important to note that if you include dimension 3 terms, you can possibly recover a cosmological background. So yeah, that would be important to try to look at as well, although it becomes more challenging to do the calculation in our approach. And our notion of locality, if there's no instantaneous signaling, may become more subtle on such non-trivial backgrounds. But these are all other things that one could look at. And that's all I have to tell you about. So thank you very much for your attention, and I'm happy to answer any questions.
Okay, thank you very much for the nice talk. Is there any question from the audience? Maybe in case somebody's typing. You considered continuous deformations of Lorentz invariant theories by adjusting parameters. Can you have comments on some extremely different theories like Hojava-Lifshitz gravity, if you're familiar? It has some inhomogeneous scaling between temporal and spatial kinetic terms.
I'm not sure how well I can comment, but
If it's consistent with locality or whatever principle.
yeah, the only assumptions that we make when we write down this action plus mass terms are spatial rotations and translations. So yeah, maybe I'm not familiar with what you're trying to ask, but is there something else that you think we could include?
It's okay. Yeah. Do you see another question on the text in the chatting text?
Yes. So the question is it possible to relax your assumption about 2 degrees of freedom? So yeah, maybe this is what you're getting at as well. So Harava type gravity has this dispersion relation omega squared equals k to the 4. And so, yeah, one could say only assume 5 degrees of freedom if one wanted to include masses as well. But that's right, our assumption here is that we're studying spin 2. So if we choose to study spin 2, then we have 2 degrees of freedom, or maybe 5 degrees of freedom if we want to say that. But if we start adding other degrees of freedom, then okay, maybe we have spin 2 plus a scalar or something, which one could of course also do. But yeah, our choice here is that we wish to study spin 2. So that's our setup.
Okay, thank you very much, Jacob, for the nice talk.
Thank you.
Okay. Our next speaker will be Kevin Cale. I see he's around, yes.
Let me unmute myself, and my talk is over here in a PowerPoint. I'm not quite sure how to put this PowerPoint on that slide. Is that?
Can you share your screen or your slide? There's a button at the bottom. Maybe it's a green button. Share your...
Right. I see the green button. So I'm going to hit share screen, but now I need to go to this screen. Right. Share. Sorry.
Yes, I'm seeing the screen now. Okay, so are you ready to start now?
Yeah, sure. Let me just
Sure,
right.
Let's start. Yeah. So the next speaker will be Kevin Cahill, and he'll talk about local Lorentz invariance and dark matter. Please go ahead.
Hi. Well, good morning, people in Asia, and good evening, people elsewhere. I'm going to talk about, as the title suggests, gee, I'm not able to, I can't get the, let's see if this works. There. Okay, so I'm going to be talking about the fact that general relativity with fermions has 2 independent symmetries. One is general coordinate invariance. That's the traditional symmetry of general relativity, the well-known symmetry. And the second symmetry is not mentioned very often. I've never seen it actually, and it's local Lorentz invariance. And in traditional general relativity, local Lorentz invariance is implemented by something called the spin, oh God, I've forgotten now what it's called. The spin, I'm terrible with names. Let me just, anyway, what I'm suggesting here is that it may be implemented by bosons that have their own Yang-Mills-like action. I'm calling these L bosons, L for Lorentz. These L bosons would couple to fermions and generate a potential that violates the weak equivalence principle. Experiments have shown that L bosons, if they exist, are nearly stable and contribute to dark matter. So once again, general relativity with fermions has two independent symmetries, general coordinate invariance and local Lorentz invariance. So I'm confused as to, all right, anyway, in standard formulations, local Lorentz invariance is implemented by the spin connection. Here, this omega sub I. I'm suggesting that it may be implemented by gauge bosons that have their own Yang-Mills-like action. Such L bosons were coupled to fermions and generate a potential that violates the weak equivalence principle. And if they are massive, the inverse square law as well. Experiments looking for such potentials imply that the bosons, if they exist, are nearly stable and contribute to dark matter. Now let's see if I can go to the next slide without screwing some things up. In standard formulations, the covariant derivative of a Dirac field looks like this, where this is the spin connection. These are ordinary gamma matrices. Here I'm using a 4-component Dirac spinner. The spin connection is involves the Levi-Civita connection gamma, and then Cartan's tetrads, derivatives of the tetrads and a quadratic expression in the tetrads. The Levi-Civita connection in turn is defined in terms of derivatives of the metric tensor and the inverse of the metric tensor. Whoops. And the metric is quadratic in Cartan's tetrad. So this is the standard formulation. And what bothers me about this formulation is that this coupling to fermions is just so, frankly, ugly. I mean, look at that thing. And since the metric is quadratic in the tetrads, the spin connection, the traditional spin connection is of 6th order in the tetrads, because we have here second order, so that's 4th order, 5th, 6th order. Now, in the standard model, we're accustomed to associating a gauge field with every symmetry. And the gauge field has its own action, a Yang-Mills action. If this pattern extends to gravity, then local Lorentz invariance would have its own gauge fields, 3 for local rotations and 3 for local boosts. I'm calling these L bosons L for Lorentz. L bosons gauge local Lorentz transformations. And here then the expression of the covariant derivative acting on a Dirac spinner is like in the standard model, namely it's some sort of matrix times a vector field. And these L bosons then define a field strength as the commutator of the covariant derivatives, and they have their own Yang-Mills action. That's what I'm suggesting. Now let's look at a general coordinate transformation and the way I distinguish between a general coordinate transformation and a local Lorentz transformation. The general coordinate transformation acts on coordinates and acts on world indices. Whoops, sorry. And so a gauge field, electromagnetic field, transforms this way under a general coordinate transformation. On the other hand, the Cartan's tetrads transform this way with no change on the Lorentz index. A Dirac field under a general coordinate transformation just changes by virtue of the change in its coordinates. And the L bosons that I'm suggesting may exist transform this way just because of their one world index. A local Lorentz transformation, on the other hand, acts on Dirac and Lorentz indices, but leaves world indices and coordinates unchanged. So the electromagnetic field is totally unchanged. The Cartan's tetrads transform according to a Lorentz transformation. A Dirac spinner transforms this way with no change in the coordinates. And the L bosons transform this way like a Yang-Mills boson. Just to check that the Dirac action is actually invariant on the local Lorentz transformations, we can just recall these standard formulas for how gamma matrices play with Lorentz matrices. And from that, it follows that whoops, what happened? That gamma contracted with the Cartan tetrads is invariant. And so the Dirac action density itself just turns into this expression. And because this derivative is actually covariant, you just get a D inverse. And then this structure, this D inverse adjoint goes across via this relation. And then D inverse on the contracted gamma with the tetrad just leaves something invariant. So the Dirac action density is invariant under a local Lorentz transformation, no coordinate transformation. By the way, this is different in the case of flat space. In flat space without tetrads, there's a conspiracy between the how the Dirac matrices and the space-time transformation of a flat Lorentz transformation and flat fat Minkowski spacetime, how those things conspire to make the Dirac action invariant. Anyway, the matrix of Lorentz gauge, let's say L boson gauge fields looks like this. If you expand the Dirac matrices, it has a Hermitian part that looks like that. Now, what about these L bosons? They may be massless, and that's probably the most likely case. On the other hand, a Higgs mechanism is possible. And for example, the time component of a field that is a world scalar and a Lorentz vector, if it got a non-zero average value in the vacuum of our pocket universe, suppose it did, well, then the kinetic action of this field that I wrote as V, I guess V for vacuum, it would give masses to the three L bosons that gauge boosts. Now, if the L bosons are massless, then experiments show that their coupling to fermions is very weak. Now, in fact, no experiments have been done looking precisely for L bosons. Instead, what's been done is experiments looking for bosons of or departures from Newton's law of gravity or from Einstein's law of gravity. And the limits on these are very, very severe. And consequently, the L bosons, if they exist and are massless, they interact very weakly of order gravitational weakness. And so they were not in thermal equilibrium in the early universe unless our pocket universe was had reached Planck temperatures. So they don't affect the transition from the era of radiation to the era of matter. On the other hand, if the time component of this field D, that's a world scalar and a Lorentz vector, if it is non-zero, well, the change in the angular momentum generators looks like this, and it basically commutes with the parts of the fields of the standard model, so it wouldn't really show up any breaking of angular momentum. Now, massive L bosons coupled to fermions and make Yukawa potentials, and the standard way to, or a standard way to parameterize these is to, or at least the way I do it for the case of L bosons as opposed to general fifth force bosons, is with a parameter alpha, a scale lambda, and mass factors out in front. But this alpha has to do with how many fermions are in a given mass and also a coupling constant. Now, I'm going to review some of the experiments. The Riverside and Indiana and Purdue group have placed upper limits on the strength of Yukawa potentials that violate the inverse square laws at differences, at short distances between 1/100th of a micron and 100 microns. So those were quite remarkable experiments. The Washington group tested the inverse square law at slightly longer distances between a micron and a millimeter. A Chinese group, interestingly enough, at Wuhan, tested the inverse square law from 2 microns to 3 millimeters. And the Washington group tested the weak equivalence principle over longer distances from 1 centimeter to 10 to the 13 meters. And so you see these limits are that the strength is quite weak. Recent measurements by the microscope satellite mission have lowered the upper limit on the strength of Yukawa potentials that violate the weak equivalence principle by about an order of magnitude, again, between 1 centimeter and 10 to the 9th meters. So summarizing all that data, what we can say is that there's a region that's excluded, and the scale for these various scales in meters from 10 to the -9 to 10 to the 9th, that's 18 orders of magnitude. And here, 30 order of magnitudes of strength. This is basically what's allowed, the white region. And this region in here is a region in which massive L bosons would contribute something to dark matter, but not all of dark matter. On the other hand, if we're over here, the L bosons would contribute more than the known amount of dark matter. So I think the summary is that L bosons were in massive L bosons were in thermal equilibrium at very early times. Experiments put upper limits on the strength of the potential between fermions for L bosons of a given mass. These L bosons therefore interact weakly and decay slowly, and therefore are still around. So the experimental upper limits, in a curious way, point toward dark matter, not away from it, because they say that if massive L bosons exist, they're still here. Experiments put lower limits on the masses of L bosons that interact with a given strength. And whether massless or massive, the L bosons contribute to dark matter if they exist. On the other hand, the contribution of massless L bosons would be very small. I'm afraid that this is a duplicate slide, effectively. Conversations with Ruzba Alaverdi, Francis Yan Sirosine, Bobby Middleton, and Leanne Yenavu improved this talk. And here's the first page of that paper that describes all of this in much more detail. And on the left is an advertisement for the second edition of my book on mathematics. So I gather that I have ended early, which I hope doesn't upset the schedule.
That's good. Thank you very much. Thank you very much. Thank you very much for the talk. Is there any question from the audiences? We have a couple of minutes for questions and answers. I don't see questions from the text yet. Hope nobody's texting. If no more questions, then let's thank Kevin again for the nice talk. Thank you very much.
Bye.
Good. We have our next speaker. Yes, Toshi.
Yes, I'm here.
Yeah.
Let me share my window. Do you see my slides?
Yes, I do. Yes.
Okay, great.
Okay, so the last speaker of this session will be Toshifumi Nomi. He'll talk about gravitational positivity bounds and the standard model. Please.
Yeah, thank you very much for introduction. I'm Toshifumi Nomi from Kobe University. Today, I'm going to talk about this paper with these collaborators about gravitational positivity bounds and its implication for standard model. So here is an outline of my talk. So my talk is about the so-called positivity bounds on low energy scattering amplitude, which provides a criterion for low energy FT to be UV completable in the standard manner. And in particular, when applied to gravitational EFTs, this provides a swampland condition. And actually, recently, there was an interesting paper by these people, which is about implication of positivity to QED coupled to GR. And they found some several puzzles. And motivated by this work, we extended the analysis to the standard model. And as I explain later, we resolved some of the puzzles in this context. So this is the outline of my talk. And in the following, I will explain these three things one by one. Okay, so let me start from positivity bound. So the basic idea of positivity bound is to relate UV and IR by using fundamental principles such as unitarity. And in this context, an important question are what are consistency conditions for EFT to be UV completable? And in particular, it is another interest is in clarifying where is the cutoff scale lambda, where the UV completion has to happen. And positivity bounds provide a quantitative criterion for quantitative answers to this question by using consistency of scattering amplitude. So let me explain this idea. So in this slide, I will focus on non-gravitational theory for technical simplicity, but I will explain the situation for gravity shortly. So having QED in mind, let us consider photon-photon scattering in the forward limit. And in this figure, I plotted analytic structure of this amplitude. So this is a S-channel branch cut associated with multi-particle states, and this one is a U-channel counterpart. And if you are interested in IR theory, we can expand amplitude in this way in Mandelstam variable. And for example, this coefficient C2 of S squared is given by the integral around the origin like this. So this is the language of IR. And in order to relate this IR information to UV data, we can deform the integration counter like this. So this is a expression after counter deformation. So here the first term is an integral along the branch cut. And I use the SU crossing symmetry to relate U-channel branch cut to the S-channel one. And the second term is integral at the infinity. So in this expression, everything is given in terms of UV theory. Okay? And if we further assume that the amplitude is bounded by a square, which is motivated by Flusser bound, then the second term vanishes. And so the IR coefficient C2 is directly related to the integral over the discontinuity like this. And optical theorem says that this imaginary part has to be positive, and so C2 has to be positive. And this is a famous positivity bound. So to summarize so far, unitarity and analyticity implies a positivity bound in this form. And actually, it is convenient to decompose this integral region below and above the cutoff scale in the following way. So here I introduced a new quantity B lambda, which is C2, this is the coefficient of S squared, minus integral up to cutoff scale. And this guy has to be equal to integral above cutoff scale, and which has to be positive because of unitarity. And an important point is that this B lambda is calculable within EFT because C2 is IR coefficient, and also this amplitude is below the cutoff scale. And another remark is that B lambda monotonically decreases as lambda increases. So the discussion so far is about non-gravitational theory. And actually, if we want to generalize this to gravitational theory, there are some subtleties. But even though I will skip details today because of time limitation, but what we can say is that if we assume weakly coupled UV compression of gravity and what we call single scaling behavior of ledge amplitude, then one can derive the following approximate positivity. So here, MS is a mass of higher spin-rate state. So if you are interested in this detail, please look at our paper or very nice paper by Tokuda, Aoki, and Hirano. So anyways, so if we, by using consistency of scattering amplitude, we can show that this B lambda, which is a quantity calculable within EFT, has to be approximately positive. So this is a positivity bound. Okay. So now let me explain its implication for QED coupled to gravity, mainly based on this paper by the Imperial group. So the idea is the following. So let us suppose, let us identify QED coupled to GR as a low energy EFT. And then we can ask if this, this gravitational QED is UV completable or not. And in particular, we can also ask where is the cutoff scale of this theory. And to answer this question, we can use gravitational positivity introduced in the previous section. So as I mentioned, the positivity says that this quantity, which is calculable within EFT, has to be approximately positive. And so to compute this amplitude, we can use QED coupled to GR. And actually, there are only three types of relevant diagrams at the leading order in the loop expansion. So here, this guy is a QED box diagram, which exists even in the non-gravitational theory. And on top of that, we have a GR contribution. So this one is graviton exchange, and this is one loop correction to graviton exchange diagram. And on top of that, we have some contribution from degrees of freedom above the cutoff scale. So this is the amplitude, and based on this diagram, we can compute the quantity B lambda, and we can discuss implication of positivity. So let me call the quantity B corresponding to each diagram like BQED, BGR, and BUV. And now it is straightforward to compute this quantity B. And so by noticing that QED amplitude is bounded by a square at UB, we can show that C2 is given by some integral like this. And afterwards, we can show that this BQED is given by integral of this box diagram from lambda square to infinity. And after some computation, we can show that this quantity is bounded by lambda to the fourth. So this is a contribution from QED diagram. This is bounded by lambda force. And another contribution coming from GR diagram, which is given like this, it's given like this. So it is straightforward to compute this thing, but the important thing is that this guy has a negative sign. And on top of that, this guy stays finite even in lambda to infinity limit. So this is a two main contribution to the inequality. So all in all, the gravitational positivity bound implies this inequality. So this one is a contribution from QED, and this is from GR, and this is from UV degrees of freedom. And this is some ambiguity associated with subtlety of gravity. But noticing that electron mass has to be way below the cutoff scale, then we can simplify this inequality into this form. So as you can see here, the left-hand side is bounded by 1 over lambda force. On the other hand, the right-hand side is lambda independent. And as a consequence, we can give an upper bound on the cutoff scale lambda like this. So this is the cutoff scale of the gravitational QED. And if we apply the QED value over real world, this guy turns out to be 10 to 8 GeV. So this is a main result discussed by the Imperial group, which I mentioned earlier. So to summarize, so far I used a gravitational positivity bound to discuss consistency of gravitational QED. And the bound implies a upper bound on cutoff scale like this. And the result says that the cutoff scale is like 10 to 8 GB, which is too low compared to the cutoff scale, for example. So one would wonder that this cutoff scale could be too small to believe. And another interesting puzzle is that if we take massless limit of this bound, meaning ME goes to 0, the cutoff scale lambda goes to 0. So it sounds like massless QED is in the swampland, which sounds like a bit strange. So, to solve these puzzles, we extended our analysis to the standard model. Okay. So now let me advertise our work, finally. So what we did is basically the same as QED case, and we used gravitational positivity bound to discuss consistency of the full standard model. And what to do is basically the same as QED, but there are two important differences. The one difference is that in contrast to QED, we have spin-1 charged particle in weak sector, namely double bosons. And another remark is that there can be hadrons if some of the Mandelstam variables are below the QCD scale. So this is the main ingredient. So let me explain contribution from weak sector and QCD sector one by one. So let me start from weak sector analysis. So if we look at weak sector amplitude, we have this type of one loop diagram like this. So this is just a box diagram, and we have something similar. And essentially because of spin-1 nature of the double boson, the high energy behavior of this amplitude is given like this. So this guy behaves like S linear in S. So on the other hand, QED amplitude was S to the zeros. So essentially because of this difference, the bulk quantity B has a suppression only 1 over lambda square. So previously QED quantity has a 1 over lambda force. So at high scale, weak sector dominates over the QED effect. So this is a QED weak sector analysis. And also for QCD sector analysis, actually we have to look at the non-perturbative effect of QCD carefully. So the quantity B is given by integral of the imaginary part of the amplitude at high energy. But the important thing is that we are looking at forward limit so that the Mandelstam variable T is smaller than the QCD scale. So essentially because of this, we have to look at hadron effect carefully. And after taking into account this effect, we find this type of behavior. And here is a summary of the result. So the gravitational positivity bound implies this type of inequality. And this right-hand side is plotted by this black dotted line. And this red one, blue one, and green one are contributions from QED, weak sector, and QCD sector. And the hand side has to be bigger than the black one. So it shows that the maximum cutoff scale of the standard model is 10 to 16 GB or something like this. So which improved the QED cutoff scale in a significant way. So as a final remark, let me comment on a hypothetical electronic theory without QCD sector. And if we don't have QCD sector, what we compare is this blue line and black dotted line. And the positivity bound given by this inequality can be rephrased like this. So it provides an upper bound on the ratio of double boson mass and Planck mass in terms of electron mass and cutoff scale lambda. So one could imagine that one could expect that this could provide a possible explanation for hierarchy between the electroweak scale and the Planck scale. And another important remark is that this inequality shows that massless limit of QED, namely M equals to 0, can be consistent if we take double boson to massless. And actually, this is consistent with the deep picture of the string theory. Okay, so let me summarize my talk. So in this talk, I discussed the implication of positivity bound in gravitational theory, motivated by recent swampland activity. And so when we apply this to gravitational QED, there are some puzzles, like cutoff scale is too small compared to cutoff scale, etc. And also massless QED was in the swampland. But we showed that we extended the analysis to the standard model, and then we found that the cutoff scale is improved up to lambda to 10 to 60 GB, which is close to the cutoff scale. And also we found that massless limit of this QED is allowed if we take a double boson goes to 0 simultaneously. Okay, that's all my talk. Thank you very much.
Okay, thank you very much for the nice talk. You already have one question. Can you read the chatting?
I
think
see.
the question
How
was raised
one
at
can-
the security part.
I see. How one can know the value of MS, although it is heavier than the cutoff scale lambda? I see. Yeah, thank you for the question. So, yeah, okay, so there is no, we cannot know the value of string MS. So what we know is, what we know is that MS has to be higher than lambda, or higher or equal to the lambda. And this is enough for our analysis.
Any other questions?
Can I ask something? Can I use this instead of writing?
Yeah, sure, please.
Okay. Can you say something more about this single scaling limit? This is what allows you to do the integration above the cutoff, right?
Right. Yeah. That's right. So, yeah, thank you for this point. So single scaling assumption is, okay, so in order to give a bound in gravitational theory, we have to assume ledge behavior of the amplitude. And so here I parameterize ledge amplitude like this at high energy. And our single scaling assumption is that dimension-free parameters appearing here, F or alpha prime, are basically the string scale. And because of this assumption, we obtain a bound on B lambda like this. So in order to get a lower bound in terms of string scale, we needed this assumption. Would it answer?
Yeah, so this is how it looks in string theory. Like this is the Regge trajectory of string theory, roughly?
Yes.
And
So it
then this
doesn't
is
mean
what
that
cuts off the integral that you're doing. Sorry, this is what cuts off the integral that you are doing because you're extending the integral above the cutoff.
Right. This is used to evaluate integral from cutoff to infinity. So especially when we discuss behavior around the infinity, we need this information.
Thank you.
Okay. Any other questions?
Do you mean that the positivity bound P can be understood as? Yeah, thank you for this point. So yeah, probably I should explain. I should have explained it more carefully. So this is a result without making any assumption. And now we can compare this thing and this thing. So yeah, when we compare these two things, the contribution from this guy always dominates over this ambiguity. And the assumption like ME is much below the cutoff scale. This is what I mean. Would it answer to your question? Yeah, thank you very much.
Any more questions?
May I ask? Hi. Sorry. Froissart bound cannot apply for the string theory?
Okay. Yeah, thank you for this point. So in the standard derivation of Froissart-Martin bound, we have to assume that the theory has a gap. So in massless theory, it does not apply. But what we know is that string theory satisfies Froissart-Martin bound. So I mean, the standard derivation does not apply to massless theory, but no example of UV complete quantum gravity satisfies this property.
Thank you very much.
Okay. Okay. If no more questions, let's finish by thanking Toshifumi again.
Yeah, thank you very much.
Yeah, we're going to close this session by thanking all the speakers of this session. Thank you all. Okay, thanks a lot.